Welcome to the Deep Dive, the show where we cut through the noise and get straight to the knowledge you need. Today, we're plunging into a topic that's often seen as purely technical, but which actually has profound strategic, economic, and, well, even innovative implications. We're talking about IPv6 on Amazon Web Services. And this isn't just about some, address upgrade. It's really a fundamental shift in how we build, secure, and scale cloud infrastructure for the demands of tomorrow. Okay, let's unpack this.
Exactly, and the core problem that IPv6 addresses is this undeniable reality of IPv4 address exhaustion. It's a challenge the internet's been grappling with for, gosh, well over a decade now. But what's truly compelling, I think, is how AWS has positioned itself as a real key player in this transition. They offer robust and, importantly, continually expanding support for IPv6. They give you a clear, practical path forward for organizations looking to modernize their networks. You can go for a hybrid dual-stack approach, or maybe even go all in with IPv6-only configurations for those really cutting-edge workloads.
Right. And our mission for you, our listener, is clear today. By the end of this deep dive, you won't just understand what IPv6 is. You'll really grasp why it's no longer some distant future thing, but an immediate imperative, especially for modern cloud architectures, particularly within AWS. We'll arm you with practical knowledge, the strategic why now, and hopefully some genuinely surprising insights, things that will shortcut you to being truly well-informed. Just to start, let's consider the sheer mind-boggling scale difference here. IPv4 gives us, approximately 4.3 billion unique addresses?
Around that, yeah.
Yeah.
Seems like a lot, but...
But IPv6, we're talking about an astronomically vast number, 3.4 times 10 to the power of 38 unique addresses. To put that into perspective, it's enough to give every single atom on Earth billions of IP addresses. Yeah. Billions. And you'd still have trillions upon trillions left over.
Almost impossible to comprehend, really.
Exactly. So this isn't just about more addresses. It's about unshackling innovation. Imagine architecting a network where you never, ever have to think about IP address scarcity again, where every device, every sensor, every tiny microservice can have its own globally unique identity right from day one. That foundational freedom, that's the true aha moment of IPv6, I think. So let's maybe set the historical stage a bit. The internet's growth, it's been nothing short of explosive, hasn't it? Truly beyond what anyone could have possibly imagined back in the early days.
Absolutely. Unprecedented.
And this incredible expansion, while wonderful, has inevitably pushed us toward a very real wall. IPv4 address exhaustion. IPv4, the original standard, operates on that 32-bit addressing scheme. That gives us that finite pool, roughly 4.3 billion addresses. Now, that might have seemed unimaginable in the 80s.
A lifetime ago in tech terms.
Right. But it's become demonstrably insufficient today. And the truly crucial point here, I think, is that the last available block of new IPv4 addresses was actually allocated by INA way back in 2011.
2011. That's quite a while ago now.
It is. Since then, it's just been this game of increasingly costly reuse, resale, and careful conservation. It's created this highly constrained and, frankly, expensive global market for these digital identifiers. And just think about what this means in our modern world. The relentless proliferation of connected devices. Everything from the smartphone in your pocket, your smart home stuff, to billions, literally billions of industrial IoT sensors churning out data. And then you've got those ever-growing, highly distributed cloud-native applications that power our daily lives.
Everything needs an IP?
Exactly. Each of these requires an IP address, and IPv4 has just been stretched to its absolute limits trying to accommodate them. It's simply inadequate for modern network growth. You can easily picture this Internet of Everything idea, right? Where billions, maybe even trillions of interconnected devices are constantly talking, creating this intelligent global fabric. The massive connectivity requirements there are fundamentally impossible to support on IPv4's limited space. It just wasn't built for that scale.
You've really hit the core problem perfectly. And for a long time, the discussion around IPv6, well, it acknowledged the long-term necessity, but it felt a bit abstract for many organizations, didn't it? It was like a future strategic priority, maybe, but not an urgent, immediate business problem.
Yeah, something for down the road.
Exactly. But that dynamic has fundamentally, and I mean very rapidly, changed. The single most significant catalyst, I'd say, for accelerated IPv6 adoption today, especially within the AWS ecosystem, is the introduction of those new charges for public IPv4 addresses. These charges, they became effective back in February 2024. And they basically transformed what was this long-term sort of abstract concern about address exhaustion
into cold, hard cash.
Precisely, into a tangible, recurring, and often quite substantial expense for AWS users. And this financial pressure, it isn't just a gentle nudge. It's really serving as a direct, undeniable catalyst for network teams, for business leaders to prioritize IPv6 adoption. Suddenly, the goal isn't just future-proofing. It's also directly reducing operational expenditures, avoiding the overhead of these complex, constrained IPv4 architectures. Cost reduction has become a direct, measurable goal that CFOs and technical leaders can both understand and champion.
Makes the conversation a lot easier, I imagine.
Definitely. And the financial motivation for adopting IPv6 is especially pronounced for organizations with large-scale deployments, right? Ones that rely heavily on public-facing endpoints or maybe need extensive outbound internet access. Because every additional public IPv4 address now incurs that direct hourly cost. What's truly fascinating here, I think, is how quickly a theoretical problem can hit the bottom line and become an urgent business priority. It demonstrates a powerful principle, really, about how market shifts, even those driven by long-standing technical realities, can quickly turn these abstract technical problems into compelling, immediate business drivers. It's really no longer about if you'll move to IPv6, but when and how strategically you'll do it.
That economic incentive is incredibly powerful, absolutely, no doubt about it. But what's truly exciting, I think, is that beyond just sidestepping the IPv4 crunch, IPv6 isn't just about solving a problem. It's about unlocking capabilities that IPv4 could never even dream of. It genuinely streamlines network operations and enhances what's possible in the cloud. It offers inherent technical advantages far beyond just having more addresses.
That's a key point. It's not just about quantity.
Right. Let's delve into some of those fundamental shifts. With IPv4, we're constrained by that 32-bit address size, yielding those 4.3 billion addresses we talked about. IPv6, as we mentioned, makes that massive leap to a 128-bit address size. Huge difference. The naming standard shifts, too, from the familiar dot decimal numerical format, like a 192.0.2.1, to a more complex but vastly more expansive alphanumeric hexadecimal format, something like 2001.db8 on 85A3.82E.0370.7334. Looks complicated at first glance.
Takes some getting used to, for sure.
It does, but it's not just about size or format. IPv6 was actually thoughtfully designed with built-in security features and architectural improvements right from the start, which is quite unlike its predecessor, where security often felt like it had to be bolted on afterwards, didn't it?
It really did. And you've hit on a critical point there. One of the most significant architectural advantages of IPv6 is the elimination of network address translation, or NAT, in most scenarios. To truly appreciate this, let's just remember why NAT became so prevalent in the IPv4 world. It was an ingenious workaround, Band-Aid, really, wasn't it? To artificially inflate the address space.
Yeah, stretch those last few addresses out.
Exactly. It allowed multiple private addresses within an internal network to map to a single public IP address for internet communication. Now, while it saved IPv4 addresses, this process adds considerable performance overhead and complexity to network design. It really does. Every packet has to be translated. That slows things down, consumes CPU cycles on the NAT device, and makes troubleshooting.
Well, a genuine headache sometimes because the true source or destination IP is masked.
Been there, trying to trace a connection through NAT layers. Yeah, it's not fun. But with IPv6's truly vast address space, every address can be globally unique and directly reachable. This removes the fundamental need for NAT and all its associated translation overheads. And that significantly simplifies network architecture, reduces latency, and improves overall performance through more direct, efficient communication paths. If we connect this to the bigger picture, removing NAT is actually a monumental shift. It fundamentally changes how we design and scale cloud networks. Imagine the architectural freedom, right? No more worrying about overlapping CIDR blocks in your VPC peering connections because every subnet can have a globally unique, massive IPv6 range. And beyond just eliminating NAT, IPv6 also introduces stateless address auto-configuration, or SLAC.
SLAC, right? That sounds helpful.
It is. And it isn't just about simplicity. It allows devices to self-configure their own IPv6 addresses without needing a centralized DHCP server. Now, this is incredibly powerful for massive dynamic IoT deployments or ephemeral cloud environments, maybe edge computing scenarios, because it removes a central point of failure and significantly reduces the management overhead that DHCP often introduces. It makes networks more resilient, more self-organizing.
Less manual configuration, less chance of error.
Precisely. And those routing efficiency enhancements we mentioned earlier. The fixed 40-byte header in IPv6, compared to IPv4's variable 2060 bytes, means routers can process packets with predictable speed and lower overhead. The seemingly small detail actually translates to real-world performance gains, especially in high-traffic, latency-sensitive applications. Couple that with IPv6's inherent hierarchical addressing capabilities, which allow for efficient route summarization, and you basically have a recipe for more performant and manageable global networks.
And what's truly transformative about IPv6, I think, isn't just in the numbers, the scale, or even the efficiency gains, important as they are. It's how it unlocks the very technologies that are defining our future. Think of it as a critical enabler for the Internet of Things, right? That vast, sprawling network of billions of interconnected devices, smart home gadgets, industrial sensors.
Everything talking to everything.
Exactly. These devices are constantly generating and communicating data, and they simply cannot be supported by IPv4's limited address space. IPv6 gives them a globally unique identity from birth. It also provides the necessary scalability and address density for 5G networks. That paves the way for next-generation applications needing ultra-low latency and high bandwidth. Things like augmented reality, virtual reality, other immersive experiences where every millisecond counts. Imagine autonomous vehicles needing direct, low-latency communication with traffic infrastructure that's an IPv6 world.
It really opens up possibilities.
It really does. And for cloud-native applications, which are increasingly distributed and ephemeral, IPv6 significantly simplifies these large-scale microservice and container deployments. I mean, consider the nightmare of managing complex, non-overlapping IPv4 address ranges across thousands of pods in a rapidly scaling Amazon EKS cluster. It can become a huge operational burden that just detracts from innovation.
Oh, absolutely. IP address management in large container environments on IPv4 is a major pain point.
But IPv6 makes it easy. You can assign contiguous, virtually limitless IP ranges to pods and containers. You overcome those inherent IPv4 address limits and the pain of constantly re-architecting your subnet space. For example, in EKS, IPv6 lets you assign up to 250 pods per node. That's a massive increase, far exceeding typical IPv4 limits. This means architects and developers can focus squarely on application logic, building resilient systems, driving innovation, rather than grappling with network complexities and address management constraints. It truly unlocks potential and accelerates the pace of development.
Okay, so let's shift our focus now to how AWS specifically blueprints and integrates IPv6 within its cloud environment. We should start with the foundation, which is the Amazon Virtual Private Cloud, or VPC. As you know, your Amazon VPC is that dedicated, logically isolated virtual network where you launch and manage all your AWS resources. It's the fundamental building block, the core of your AWS network. Exactly. It's where you define IP address ranges, create subnets, configure route tables, security groups, all those essential network controls. The key when we talk IPv6 is that a VPC can now operate in what's called dual stack mode. That means it has both an IPv4 and an IPv6 CIDR block associated with it.
So running both protocols side by side.
Precisely. And in this crucial configuration, IPv4 and IPv6 communication are entirely independent. Resources within the VPC can then communicate over both protocols simultaneously, choosing the appropriate one based on the destination. This dual stack approach is particularly valuable for organizations undergoing those phased migrations we talked about. It allows them to maintain compatibility with legacy IPv4 systems while gradually integrating and testing IPv6 capabilities, all without a hard cutover. Now, when you enable IPv6 for a VPC, AWS typically assigns a 56 IPv6 prefix to it. This comes from its own managed address pool. And if a 56 prefix is quite generous, it provides an enormous amount of address space. While this can be expanded or customized by associating additional CIDR blocks, it's an important consideration that once IPv6 support is enabled for a VPC, it cannot be disabled.
Ah, okay, so it's a one-way street once you commit.
That's right. It underscores the commitment to IPv6 once you make that decision. Now, subnets within that VPC, however, they are fixed at a 64 prefix. This isn't arbitrary. It's a standard practice for IPv6. It's designed to support stateless address auto-configuration, SLAC, and to ensure compatibility with various AWS services and common network designs. And just to give you a sense of scale again, a single VPC can actually be associated with up to 5 IPv6 CIDR blocks. So truly immense room for expansion as your network needs grow.
Okay, so you've got the VPC set up maybe in dual stack mode. How do you actually get those IPv6 addresses? And how do you manage them? What are the practical options within AWS? Well, there are 3 primary methods available, and each is really tailored to different organizational needs and levels of control. First, and often the simplest, probably the most recommended for most use cases, is the Amazon-provided IPv6 CIDR. With this option, AWS just automatically allocates a publicly routable 56 IPv6 prefix for your VPC straight from its own address pool. It's straightforward, fully managed by AWS, and ideal if you don't already own or need to bring your own IPv6 space. You just select the option, AWS handles it. Easy.
Simple is good.
Simple is often very good. The second option is bring your own IP, or BYOIP. This is designed for organizations that already own IPv6 address blocks and want to import them into AWS. For instance, you could bring a 48 public prefix per region, or maybe a 60 for non-public prefixes. This method is perfect if you need to maintain continuity with your existing IP addressing schemes, maybe adhere to specific compliance requirements, or just leverage an address block you already globally advertise. It offers a level of consistency that's often critical for large enterprises.
Right, for established networks.
Exactly. And finally, we have the IPM-allocated IPv6 CIDR. This leverages the robust capabilities of AWS IP Address Manager, or IPM. IPM helps you centralize, automate, and simplify IPv6 address space management across multiple AWS regions and accounts. This method offers the highest level of control and governance, really, for large-scale, complex deployments. It allows you to define your own custom IPv6 address pools and then allocate prefixes to your VPCs and subnets from those managed pools. It's the enterprise-grade solution.
For managing things at scale.
Precisely. So, quick summary. Amazon provided is simple. A public 56 managed by AWS. BYOIP lets you bring your own 48, maintaining consistency, and IPM gives you that centralized control and governance for complex multi-account setups.
Expanding on that, AWS supports 3 distinct VPC and subnet configurations. Each plays a specific role in a network modernization strategy, and each offers different architectural characteristics. First, you've got the familiar IPv4-only model. That's the traditional setup you're likely already using, no IPv6 capabilities enabled, simple, legacy. Then there's the dual-stack configuration, which, as we've said, is currently the most common model for migration. In this setup, subnets within your VPC have both IP4 and IPv6 CIDRs associated. This allows resources launched into these subnets to communicate over both protocols, which is crucial for that gradual transition, letting your apps interact with both IPv4 and IPv6 services seamlessly.
The bridge between old and new, essentially.
Exactly. Finally, we have IPv6-only subnets. These subnets are configured with only an IPv6 CIDR block. Resources within them communicate exclusively over IPv6. This is where you really start to unlock the full simplification benefits of IPv6. Now, there's noteworthy technical detail for these IPv6-only resources. While they don't have a routable IPv4 address, they are actually assigned an IPv4 link local address.
A link local, like the 169.254 range.
Exactly, from the 169.254.0.016 range. This isn't for general internet communication, though. It's a specific internal mechanism for communication, with a few specific VPC services that might not yet fully support IPv6 end-to-end. It just ensures foundational AWS services can still interact with your IPv6-only instances without requiring you to maintain a full IPv4 stack. This IPv6-only model is really ideal for greenfield, cloud-native applications, new microservices, or containerized workloads that have zero legacy IPv4 dependencies and can fully leverage the streamlined IPv6 architecture.
Okay, that gives a clear picture of the architectural models. But when we start thinking about connecting those IPv6 resources, to the wider internet, or even just securely within our VPCs, what are the core networking components on AWS we absolutely need to understand, and how do they differ from our traditional IPv4 gateways? Right, let's break down the gateways. For public subnets, the Venerable Internet Gateway, or IGW, is still your go-to component. It provides that bidirectional communication with the internet, and it does it for both IPv4 and IPv6 traffic. It's the standard entry and exit point for internet routable traffic to and from your public-facing resources. Simple enough, serves both protocols.
Familiar territory for most.
Exactly. But then we introduce a crucial IPv6-specific component, the Egress-Only Internet Gateway, or EIGW. This is a really critical piece of the puzzle, specifically designed for private IPv6 subnets. Unlike the IGW, it allows outbound-only communication from your private IPv6 resources to the internet, while explicitly blocking any unsolicited inbound traffic. Think of it like a one-way door to the internet just for your IPv6 workloads.
Outbound only. That's the key difference.
It is, and it's absolutely vital to directly contrast the EIGW with a NAT gateway, which you're probably familiar with from the IPv4 world. A NAT gateway is strictly for IPv4 only outbound internet access from private IPv4 or dual-stack subnets. It performs that private to public IPv4 address translation, and significantly, it incurs data transfer charges.
Ah, the cost factor.
Right. The EIGW, on the other hand, for your IPv6 traffic, does not charge for data transfer. This is a profound architectural and economic benefit, especially for organizations with significant outbound traffic from their private IPv6 subnets. It can lead to substantial recurring cost savings. It eliminates one of the major networking costs associated with IPv4. Just remember, though, the NAT gateway still exists and is necessary for your IPv4-only outbound traffic needs from dual-stack or IPv4-only private subnets.
So you might need both in a dual-stack private subnet.
Potentially, yes. If you have both IPv4 and IPv6 resources needing outbound internet access from the same private subnet, you'd route IPv4 traffic 0.0.00 to the NAT gateway and IPv6 traffic 0.0 to the EIGW. So, to recap, public IPv4 or IPv6 use an internet gateway. Private IPv4 needing outbound internet, use a NAT gateway with costs. Private IPv6 needing outbound internet, use an egress-only internet gateway, no data transfer costs, secure. Oh, okay, let's move beyond the technical necessities and talk about the truly tangible rewards, the benefits of adopting IPv6 on AWS. It's not just about addressing that looming public IPv4 exhaustion, important as that is. It also powerfully tackles private address scarcity, which, can become a very real headache in large, complex VBCs. Those are limited to about 16 IPv4 CIDRs, right, which yields roughly 300,000 addresses total. For massive enterprises, that can actually become a constraint pretty quickly.
Surprisingly quickly, something.
Yeah. IPv6, quite frankly, just blows those limitations out of the water. It offers a completely different paradigm for network scaling.
Indeed. The scalability and performance gains are really substantial. IPv6 enables truly horizontal scaling without those traditional NAT-induced bottlenecks we discussed earlier. And this often translates directly to improved TCP throughput, particularly over those long-haul network paths where translation overheads can really add up. To put this in a, staggering perspective again, a single 56 VPC CIDR in IPv6 yields 256 64 subnets. And each one of those subnets provides approximately 1.8 times 10 to the 19 addresses.
10 to the 19 per subnet.
Per subnet. That number is, for all practical purposes, infinite. Virtually unlimited when you compare it to IPv4's mere 65,000-ish addresses per subnet. This fundamentally changes how you think about subnet design. It eliminates the need for complex VLSM constantly carving out tiny blocks. It's just gone. And consider these real-world examples. Amazon CloudFront's IPv6 support can significantly enhance content delivery to IPv6 clients. How always? By reducing latency and bypassing unnecessary IPv4 tunneling or translation hops. In fact, specific tests have shown potential throughput improvements of up to 20% on high-latency paths with CloudFront's end-to-end IPv6.
20% is not insignificant.
Not at all. And in container environments like Amazon EKS, IPv6 allows for, as you mentioned, up to 250 pods per node. That's a significant increase over typical IPv4 limits. This greatly facilitates massive container deployments without that complex subnet fragmentation. It makes it far simpler to orchestrate large-scale, ephemeral microservices architectures. The address space just ceases to be a constraint.
Okay, so this is where the economic incentive really kicks in, isn't it? Moving beyond just future-proofing to direct, measurable, and pretty significant savings today. By minimizing or even completely eliminating NAT usage in your IPv6 workloads, organizations can save substantially on those recurring NAT gateway charges. Remember, IPv4 NAT gateways incur data transfer charges and hourly fees.
Double hit.
Right. With egress-only internet gateways for IPv6, there are no data transfer charges. That's huge. This reduction also simplifies your infrastructure, lessening the need for complex, highly available NAT setups. AWS itself actually reports that IPv6-only architectures can lower networking costs by up to 50% in large-scale deployments.
Up to 50%. That's a massive potential saving.
It really is. The primary reason, as we highlighted, is simply the elimination of those public IPv4 allocations, which now incur direct hourly fees. These savings can quickly add up to millions for large enterprises, making IPv6 adoption a clear business case, not just a technical one. It's about optimizing your cloud spend.
And beyond the cost savings, IPv6 also significantly broadens your global reach and helps meet increasingly common compliance requirements. It expands accessibility to that growing base of IPv6-enabled devices worldwide. As of 2025, over 40% of global internet traffic already accounted for IPv6.
Over 40%, wow.
Yeah, it's climbing fast. This is crucial for reaching mobile users and preventing potential revenue loss from incompatible networks. Many cellular carriers and new broadband providers are now IPv6 first. So if your public-facing services aren't IPv6 ready, you could be offering a degraded experience, or you might simply be inaccessible to a significant segment of your potential audience. We've seen companies like Yle's Radio, a major public broadcaster in Finland, simplify debugging and accelerate innovation by adopting EKS IPv6, allowing them to serve their diverse user base more effectively. Furthermore, for many organizations, particularly those in the public sector or regulated industries, mandates like the U.S. federal requirements for IPv6 by 2025 make adoption an absolute imperative. It moves from a nice-to-have to a must-have.
No choice there, really.
Pretty much.
Yeah.
And services like AWS Global Accelerator also benefit from IPv6 support, ensuring low-latency global routing for your applications to this expanding IPv6 user base.
And let's not overlook the benefit of a truly simplified network design, especially for large, complex cloud environments. IPv6's hierarchical addressing natively supports route summarization. Now, this is a game changer because it allows you to represent huge blocks of addresses with a single, concise route. This dramatically reduces BGP table sizes in complex environments that might be using services like AWS Transit Gateway for inter-VPC routing or AWS Direct Connect for hybrid connectivity.
Less routing complexity.
Much less. All those complicated techniques like variable length subnet masking, VLSM, that were common in IPv4 just to squeeze every last address out of a CIDR block, they simply become obsolete. This fundamentally streamlines configurations across multi-region and multi-account environments, especially when managed via a tool like AWS IPAM. We're talking about a potential reduction of route table entries by like 90% in large networks. That significantly eases operational burden and improves routing efficiency.
Exactly. And these aren't just theoretical benefits, right? They are rigorously substantiated across extensive AWS documentation and numerous real-world customer implementations. It really underscores IPv6's essential role in future-proofing cloud architectures and driving operational efficiency. So just to quickly summarize some of the most compelling quantifiable impacts we've touched on. You get literally 1019 addresses per subnet. Mind-boggling. A potential for up to 20% throughput improvement on high-latency paths, and the capability to achieve up to a 50% networking cost reduction. The advantages are compelling, they're tangible, and they're directly impactful to your bottom line and your technical agility.
Okay, let's talk security. When it comes to security in IPv6 environments on AWS, it's really important to understand that it fundamentally builds upon your existing IPv4 controls and security best practices. You don't throw everything out. However, it definitely necessitates thoughtful adaptations because of the protocol's inherent differences and its new features. The good news, and a significant advantage, is that IPv6 was actually designed with security in mind right from its inception. Built in from the start, unlike IPv4's bolt-on approach.
Exactly. Its most significant native security feature is the inclusion of IPsec support as a mandatory part of the core protocol stack. This provides native encryption and authentication right at the network layer. Contrast this with IPv4, where IPsec was an optional add-on, often implemented as an afterthought or only in specific use cases, leading to inconsistent adoption. Furthermore, the sheer scale of the 128-bit address space makes it astronomically more difficult for brute force attacks to discover valid addresses on your network. Think about it. A basic brute force scan that might take minutes on IPv4 to find a target in, say, a typical 24 subnet.
Could take how long on IPv6?
Potentially billions of years on IPv6 just to scan a single 64 subnet. Now, this doesn't eliminate all attack vectors. Attackers still target services, not just addresses, right? But it significantly raises the bar for certain types of reconnaissance and direct IP-based scanning attacks. It enhances the overall security posture and reduces that noise from random probing. This inherent characteristic adds a fundamental layer of defense.
That makes perfect sense. But I often hear people say things like, oh, IPv6 security is inherently better, so I don't need to worry as much. Is that a dangerous oversimplification? Or are there genuine built-in advantages that streamline our security posture, provided we configure things correctly? And speaking of configuration, how do those core AWS security controls like security groups and network ACLs need to be adapted for this new landscape?
It's definitely an oversimplification to say you don't need to worry. Complacency is always dangerous in security.
Always.
But the built-in advantages are real, provided you adapt your controls properly. Let's talk about those controls. Security groups, SGs, function as stateful firewalls at the instance level. And here's a critical point.
Right.
By default, they deny all inbound IPv6 traffic.
Default deny for inbound IPv6. Okay,
Yeah.
That's important.
Crucial. This means explicit rules are absolutely required for any inbound IPv6 communication you want to allow. For example, if you have a web server, you need to explicitly add a rule allowing TCP port 80 from point 0, which is the IPv6 equivalent of server point 0.0.00. It's a best practice, really, to mirror your existing IPv4 rules for IPv6 and always apply least privilege principles, allow only necessary traffic. Failing to update these rules is a potential security vulnerability. You could inadvertently block legitimate traffic for your IPv6-enabled applications, or worse, unintentionally expose resources if you assume default deny is also present for outbound, which it isn't always. It's also important to remember that security group rules apply separately to IPv4 using 0.0.000 and IPv6 using 0.0.
Got it. Explicit rules needed for inbound IPv6 in security groups. What about network ACLs, the NACLs?
Right, network ACLs or NACLs. These are stateless subnet level controls, and this is another crucial distinction. Unlike security groups, NACLs default to allowing all IPv6 traffic.
Ooh, default allow. That's the opposite.
Exactly the opposite. This means you must explicitly add deny rules for any unwanted IPv6 ranges. For example, you might want to deny SC0.0.7 to avoid issues with unique local addresses, ULAs, if you're not intentionally using them and want to prevent potential routing conflicts or exposure. And let's revisit the egress-only Internet Gateway, EIGW. We've discussed its economic benefits, but it also plays a critical security role for private IPv6 subnets. By permitting outbound 0.0 traffic while rigorously blocking unsolicited inbound traffic, it effectively acts as a protective barrier, preventing direct internet exposure for your private IPv6 instances. This is especially essential in dual-stack setups to ensure IPv6 traffic is appropriately isolated and secured without inadvertently affecting your IPv4 NAT or other controls. That's a great point about the need for careful adaptation of these controls. This really raises an important question. How do we ensure our well-honed IPv4 security muscle is fully extended and adapted to this new IPv6 landscape? How do we leverage those native advantages while managing the new configuration requirements effectively?
Beyond the core controls like SGs and NACLs, AWS offers advanced security features, inspection capabilities, and crucial monitoring tools for IPv6. Services like AWS Network Firewall can be deployed in dual-stack subnets to inspect both protocols using stateful rule sets. And for centralized traffic inspection, architectures leveraging Gateway Load Balancer, GWLB endpoints, can seamlessly route IPv6 traffic through your preferred third-party or AWS firewalls, ensuring all traffic, regardless of protocol, is scrutinized according to your security policies.
So you can still inspect IPv6 traffic centrally.
Absolutely. And for web applications, AWS Wave can utilize IP sets to block specific IPv6 ranges, integrating seamlessly with ALBs to protect against common web exploits, just like it does for IPv4. AWS Shield Advanced provides comprehensive DDoS mitigation across both IPv4 and IPv6 without any performance degradation, offering always-on detection and inline mitigations. That's crucial. Furthermore, proactive threat detection services like GuardDuty and Macie are continually enhanced to detect anomalies in IPv6 traffic patterns. Things like unusual connections from broad 0.0 ranges or suspicious data access over IPv6. Tools like Network Access Analyzer can also help validate configurations for potential IPv6 route leaks, ensuring your network segmentation remains robust.
Okay, so the advanced security tooling is keeping pace.
It is. And for crucial monitoring and logging, VPC flow logs are essential for auditing dual-stack traffic. They capture all relevant IPv6 fields like source and destination addresses, ports, and protocols. You get full visibility. VPC traffic mirroring allows you to mirror full IPv6 packets to your chosen analysis tools for deep packet inspection and security forensics if you need that level of detail. And CloudWatch and X-Ray will continue to monitor IPv6-specific metrics like bytes in-out and connection counts and trace requests in your dual-stack applications, providing comprehensive visibility across both stacks. Our best practices generally include rigorous network segmentation, often achieved with private IPv6 ranges, using either ULAs or carefully managed non-advertised global unicast addresses, implementing zero-trust principles via services like AWS Verified Access, and regularly auditing your configurations with AWS Config. In dual-stack environments, a particularly important consideration is to always ensure IPv6 traffic doesn't inadvertently bypass existing IPv4 controls, for instance, maybe by disabling SLI if DHCP6 is preferred for explicit controlled address assignment in your environment.
So, to summarize those key security adaptations again, security groups are default deny for inbound IPv6, needing explicit allow rules. NACLs are default, allow for IPv6, needing explicit deny rules. EIGWs block inbound to private IPv6, a key security feature. And monitoring, inspection, and DDoS protection services seamlessly extend to cover IPv6.
All right, so you're convinced. The benefits are compelling, you understand the security nuances, and you're ready to make the switch, or at least start dipping your toes in. Now, how do you actually do it? How do you make this transition a reality on AWS? The most common and probably the most pragmatic approach for IPv6 adoption on AWS right now is configuring your VPCs for dual stack. This is particularly suitable for those transitional environments where you need to maintain seamless compatibility with existing IPv4 systems while you gradually introduce and scale out IPv6. AWS natively supports dual stack and VPCs, allowing resources like EC2 instances to get both IPv4 and IPv6 address types on their network interfaces, ENIs, functioning as true dual-home devices.
The best of both worlds during the transition.
Exactly. Now, before you dive in, just a few prerequisites. Ensure your AWS region supports IPv6, which, honestly, as of 2025, essentially all commercial AWS regions do, so that's usually covered. If you're managing multiple VPCs, especially across a large enterprise, definitely consider leveraging AWS IPM for planning your IPv6 address space. It provides invaluable centralized control and automation. And, standard practice, but worth repeating. Before making any significant network changes, always back up your configurations. It's the golden rule for a reason.
Couldn't agree more. Back up, back up, back up. Okay, with those prerequisites in mind, let's walk through a meticulous step-by-step guide for migrating an existing IPv4 VPC to a dual-stack configuration. We'll cover both console and AWS CLI actions. Step 1. Associate IPv6 CIDR blocks with your VPC and subnets. Okay, first action. Associate IPv6 CIDR block with your VPC. You have the choice, as we discussed, an Amazon-provided 56 block, simplest, or bring your own BYO IPv6 block. In the AWS Management Console, you'd navigate to your VPC, select Actions, then edit CIDRs, and finally add new IPv6 CIDR. Via the CLI, a typical command might look something like Oz EC2 associate VPC CIT CID block, VPC CIDR block to the CID, VPC-1-123-45678, IPv6 CR block network border group as East 1. You specify the CIDR, the VPC ID in the network border group region. Once your VPC has its IPv6 CIDR, the next crucial step is to associate a 64 IPv6 CIDR block from that range to each specific subnet within your VPC that requires IPv6 support.
Remember, this 64 allocation per subnet is crucial for SLA and broad service compatibility. And you can effectively have up to 200 such subnets per VPC for your initial 56 VPC allocation.
Okay, VPC gets a 56, subnets get a 64 from that. Makes sense. What's next? Routing.
Exactly. Step 2. Update route tables. While local IPv6 routes for communication within the VPC are automatically added once you enable IPv6 on the subnets, external internet access or even routing within your hybrid cloud requires additional configuration. For public subnets, you must add a route directing point 0, that's all IPv6 traffic, to your existing Internet Gateway, the IGW. This ensures your public IPv6 resources can reach the Internet. For private subnets, if you want outbound Internet access, you'll first need to create an egress-only Internet Gateway, the EIGW, if you haven't already. Once that's created, you then configure the private subnet's route table to route point 0 traffic to that EIGW for secure, outbound-only access. A CLI example for adding that public IPv6 route would be something like Oz EC2 create route table aid RTB 123456778 destination IPv6 header block 0 gateway gate IGW 123456778.
Add the default route to the right gateway. Got it. Now the crucial security step.
Absolutely. Step 3. Configure security groups and network ACLs. This is, as we stressed, an absolutely critical step, and one where misconfiguration can lead to significant security vulnerabilities or service disruption. Pay close attention here. While an outbound IPv6 rule allowing 0.000 is automatically added to the default security group when you enable IPv6, any inbound rules for your applications and any custom or modified rules you've created, both inbound and outbound, must be manually updated to include explicit IPv6 traffic rules.
Manually update all non-default rules, basically.
Yeah, that's the safe assumption, yes. The same applies to your stateless network ACLs. Remember, they default to allow IPv6, so you'll need to explicitly add deny rules for any unwanted IPv6 traffic. It's vital to stress again. This manual configuration is a potential security vulnerability if not executed correctly. You could inadvertently block legitimate traffic for your IPv6 applications, leading to outages, or, even more dangerously, unintentionally expose resources to the internet if you fail to implement appropriate inbound IPv6 deny rules. For example, to allow inbound web traffic over IPv6 to your EC2 instance, a security group rule must be explicitly added for HTTP, TCP port 80. With the source of 0.0, simply having the IPv4 rule isn't enough. You need the corresponding IPv6 rule.
Double check every rule. Okay. Step 4, getting IPs on the instances.
Right. Step 4, assign IPv6 addresses to instances. With your network plumbing configured, you can then launch new EC2 instances into your IPv6-enabled subnets. They will automatically receive an IPv6 address from the subnet 64 range upon creation alongside their IPv4 address. Alternatively, you can modify existing instances to assign an IPv6 address to their Elastic Network Interfaces, ENIs. This can be done through the console via the Networking tab for the instance, then Manage IP addresses and selecting Assign New IPv6 address. Or for automation addicts using the CLI command, AUSI-AC2 assign IPv6 addresses network interface 80i 122345678 IPv6 addresses to a 600.1f1t.1234.ab00.100. You can let AWS pick one or specify a specific address from the subnet range. This gives your instance its dual stack capability.
Okay, instance has both IPs. Final step. Testing.
Yep. Step 5. Enable internet access and testing. First, just double-check your internet gateway is properly attached to the VPC if you need public access. Then you can perform a simple connectivity test. From one of your dual-stack EC2 instances, just try ping ipv6.google.com. You should see replies coming back from its IPv6 address like 2001.4860.4860.8888. You can also use tools like curl-6, some IPv6 enabled site, to confirm HTTP/HTTPS connectivity over IPv6. If you're using Elastic Load Balancers, remember to explicitly set their IP address type to dual stack during creation or modification to enable them to listen and respond on both protocols. And always check your instance-level firewalls within the operating system itself, things like Windows Firewall or Linux IPtables and ftables, to ensure they also permit IPv6 traffic as needed.
That's a great walkthrough for dual stack. Meticulous, as you said. Now, that dual stack guide is perfect for transitional environments, bridging the gap. But for those building brand new applications from scratch, greenfield applications, there's that increasingly viable alternative, designing for a pure IPv6-only environment. In an IPv6-only VPC, resources operate with only IPv6 addresses. It completely eliminates the need for IPv4 within that VPC. This dramatically simplifies network management by removing that dual stack complexity, reducing the overhead of managing two distinct protocol stacks. Instances launched into these subnets don't even require private IPv4 addresses for general communication. This model truly allows architects to focus on a single, streamlined protocol stack, which can significantly reduce operational overhead, simplify routing, and really maximize those cost benefits we've discussed.
That said, the real world often presents that interoperability challenge, doesn't it?
Yeah.
Not all services, or maybe not all external endpoints you need to communicate with, are IPv6 ready today. To bridge this critical gap, AWS offers services like ANI64 and DNS64. These provide a crucial backward compatibility layer, allowing an IPv6-only client to seamlessly communicate with an IPv4-only server or service. The mechanism is actually quite clear.
How does that work then? NAT64, DNS64.
Okay, here's how it breaks down, step by step. 1, an IPv6-only host within your VPC, maybe an EC2 instance and an IPv6-only subnet, attempts to resolve an IPv4-only domain name. Let's say it's a legacy service that only has an A record, not an AAA IPv6 record. 2, your VPC's Route 53 resolver, provided you've enabled DNS64 on the subnet, intercepts this DNS request. If it only finds an IPv4, a record for that domain, it doesn't just return the IPv4 address. Instead, it synthesizes an IPv6 address for that destination. It does this by appending the original IPv4 address to a special, well-known IPv6 prefix, typically 64.f9e.96. 3. The IPv6-only client then receives this synthesized IPv6 address and attempts to connect to it, completely unaware it's actually talking to an IPv4 endpoint. It just thinks it's talking IPv6 to IPv4. Now, crucially, the subnet's root table must be configured to direct any traffic destined for that special 64.ff9b.96 prefix not to the Internet gateway, but to a NAT gateway. It's the same NAT gateway used for IP4. This NAT gateway, in turn, performed the IPv6 to IPv4 translation, that's the NAT64 part, converting the IPv6 request into an IPv4 request that the destination IPv4-only server can actually understand.
Ah, okay. So DNS tricks the client with a fake IPv6 address, and the NAT gateway translates it back to IPv4.
That's essentially it. While it elegantly bridges the gap, it's important to recognize that it does add a layer of complexity, and importantly, it still leverages an IPv4 NAT gateway, which incurs those costs we talked about. Therefore, for most enterprises today, the most pragmatic approach, balancing immediate needs with future readiness, is still probably to adopt a dual-stack architecture for seamless backward compatibility. It really reinforces the idea that IPv6 is not usually a forced, abrupt switch, but rather a gradual strategic transition. You build capabilities, you test, you migrate, and then, where suitable, you optimize for IPv6 only.
Okay, so we know how to implement it in the VPC. But it's really important to understand that IPv6 support, while it's rapidly expanding, still varies across the vast landscape of AWS services. This isn't like a one-and-done type of rollout where everything suddenly works, right? It requires careful planning to ensure your architectural decisions align with current capabilities and, importantly, any existing limitations. So maybe we can walk through a detailed review of different service categories, highlighting current support, architectural impacts, and any noteworthy limitations so you can guide your architectural decisions and migration planning with clarity.
Absolutely. Let's dive into specifics, starting with compute services like EC2, EKS, and Fargate. Amazon EC2 fully supports IPv6. All current generation Nitro-based instance types are compatible and can be launched into dual-stack or even IPv6-only subnets, so your basic virtual machines. Native IPv6 from day one is possible. Similarly, Amazon EKS and AWS Fargate's Container Networking Interface, the CNI, now comprehensively support IPv6 for pods and containers. This is critical for addressing that need for vast contiguous IP ranges and large-scale containerized deployments we mentioned. It unlocks those high pod density benefits. However, there is a specific and quite important nuance or limitation for EKS right now. IPv6-only clusters still must be run in IPv4-enabled subnets.
Hang on, IPv6-only clusters need IPv4-enabled subnets. How does that work?
Yeah, it sounds contradictory, doesn't it? Doesn't mean your pods themselves are running on IPv4. They get IPv6 addresses and communicate over IPv6. But it implies a dependency, likely on the underlying VPC having IPv4 capabilities for the EKS cluster's control plane, or perhaps certain internal AWS communications related to the cluster management that haven't been fully IPv6 enabled yet. So for architects, this means you can't go pure IPv6 for the entire EKS environment just yet. You need to plan your VPC and subnet strategy accordingly, ensuring you still have that IPv4 CIDR associated with your VPC, even if your workloads within the cluster are happily running IPv6 only. It's a transitional state.
Okay, important nuance for EKS users. What about storage? S3.
For storage, specifically Amazon S3, the good news is it provides dual-stack endpoints in all commercial regions. This is fantastic because it means you can make requests to S3 buckets using either IPv4 or IPv6, for instance, by addressing them via that special endpoint, s3.dualstack.region.amazonoz.com. This simplifies access for a wide range of clients, from traditional IPv4 networks to those newer IPv6-only clients. However, there's a notable limitation if you're working with S3 on Outposts, AWS's hybrid cloud offering. For S3 on Outposts, object actions like put object or get object are currently not supported over IPv6 networks.
Ah, okay. So on-prem S3 access via Outposts needs IPv4 for now.
For those specific object actions, yes. This means if you have an application running on an outpost that needs to interact with S3 objects locally and is configured for IPv6, it will likely need an IPv4 path to the S3 on Outposts endpoint for those operations. It just highlights the need for thorough architectural planning and understanding these specific constraints in hybrid or specialized edge environments.
Good to know. How about networking and content delivery? Load balancers, CloudFront?
Moving to networking and content delivery, like Elastic Load Balancers and CloudFront. Elastic Load Balancers, that includes both application load balancers, ALB, and network load balancers, NLB, have comprehensive dual-stack support. This is configurable via the IP address type option during creation or modification. You can choose IPv4, dual-stack, or sometimes just IPv6. A recent and very useful feature now allows internet-facing ALBs to be provisioned without a public IPv4 address, solely with IPv6. This is a game changer, really, as it means you can truly support IPv6-only clients end-to-end for your web applications without incurring any public IPv4 address costs for the ALB itself. Big cost-saver potential there.
That is a big deal. What about CloudFront?
Amazon CloudFront distributions, well, they can be called over IPv6 by client, so users on IPv6 networks can reach your CloudFront distribution fine. However, CloudFront distributions do not support IPv6-only origins. This means the backend server or load balancer that CloudFront forwards requests to must have an IPv4 address that CloudFront can connect to.
So CloudFront itself talks IPv6 to the user, but needs IPv4 to talk to my backend.
Currently, yes. A common workaround for this limitation involves using CloudFront essentially as an IPv6 proxy to an IPv4-only origin. This requires careful configuration of your CloudFront distribution to ensure it correctly forwards the IPv6 request it receives to your IPv4 origin. Often this involves using an application load balancer with an IPv4 target group sitting behind CloudFront.
A bit of juggling required there. Okay, serverless, Lambda, integration like private link.
In the serverless and integration space, Lambda and Private Link have seen significant advancements, which is great news. AWS Lambda now supports outbound communication over IPv6. This means Lambda functions invoked within a VPC can connect to the internet via an IGW or an EIGW without needing a public IPv4 address assigned to the Lambda function's network interface, ENI.
This is a major benefit for organizations focused on cost reduction and simplifying network architecture for their serverless workloads. No more needing NAT gateways just for Lambda outbound calls in many cases.
That's a win for serverless users and private link.
AWS Private Link, which allows you to privately connect your VPC to services hosted by AWS or by other AWS customers or partners, also supports IPv6. You can create IPv6-only and dual-stack interface VPC endpoints. This capability is particularly significant because it allows a service consumer, your VPC, to adopt IPv6, even if the backend service provider has not yet fully done so, or vice versa. It effectively decouples the adoption efforts between consumer and provider, allowing for more independent migration paths.
Decoupling adoption, that's useful. Finally, databases, analytics, RDS.
Finally, let's look at databases and analytics, focusing on Amazon RDS. Amazon Relational Database Service, RDS, supports IPv6 but only in dual-stack mode. However, it comes with a specific requirement. All subnets within the database's specified subnet group must have both IPv4 and IPv6 CIDRs attached. If even one subnet in the group is IPv4 only, RDS will not allow you to enable IPv6 for the instance using that group.
All or nothing for the subnet group, then.
Pretty much. Recent updates also include IPv6 support for the RDS Data API for Aurora, enabling IPv6 connections to your Aurora database via that specific API endpoint. A key constraint to be aware of, however, is that when RDS instances are running in dual-stack mode, they do not allow public accessibility over an internet gateway. This implies that dual-stack RDS instances are primarily designed for internal private network access within your VPC or across peered VPCs or hybrid connections. If you need to access them from outside your VPC, even for administrative tasks, you would typically use something like a Bastion host, AWS Direct Connect, AWS Site-to-Site VPN, or perhaps an IPv6-enabled private link endpoint rather than direct public internet access.
Okay, so private access mostly for dual-stack RDS.
Generally, yes. Overall, this service-by-service review really reveals a continuously evolving ecosystem. Native IPv6 support is expanding rapidly, which is fantastic, but it's not yet universal across every corner of every service. This means a pragmatic migration strategy must acknowledge today's limitations, plan for them using workarounds if necessary, while continually anticipating and planning for a future where native end-to-end IPv6 is the undisputed norm.
Okay, let's shift gears now from the theoretical and the technical how-to to some concrete real-world examples, because these case studies really illustrate that the benefits of IPv6 on AWS are not merely hypothetical, right? They translate into significant business and technical outcomes for leading organizations across various industries. It provides compelling evidence for the strategic value of this transition.
Absolutely. Seeing it in action makes a difference. Our first example is Netflix. A pioneer in cloud-native streaming, a global entertainment giant, we all know them. Their key challenge was the immense IPv4 NAT complexity and the scaling bottlenecks they faced across literally thousands of VPCs within their hyperscale environment. As we discussed, NAT adds latency and management overhead, and at Netflix's scale, this became a severe limitation.
Unmanageable at that scale, I bet.
Pretty much. Their IPv6 solution involved implementing end-to-end IPv6 with egress-only internet gateways, those EIGWs, across their vast internal network. This enabled full IP reachability for their services without needing NAT, the measurable outcome. It completely eliminated complexity and performance bottlenecks associated with IPv4 NAT. It facilitated their continued hyperscale growth, scalability, and innovation. The EIGW, as we discussed, was crucial for maintaining robust security for their private subnets while allowing essential outbound connectivity without the NAT overhead. This really shows IPv6 as a fundamental strategic asset for companies operating at the very edge of cloud scale.
Solved a core scaling problem for them. Okay, who's next?
Next, let's look at IMDb, the leading online database for films, TV, video games, also in media and entertainment. Their key challenge was a bit different: limited reach to users on IPv6-only networks. With the increasing adoption of IPv6 by mobile carriers and ISPs, they realized they were potentially missing out on a growing market segment.
Users they just couldn't reach easily.
Exactly. Their IPv6 solution was direct and effective. They successfully dialed up their IMDb TV service, now FreeV, to onboard IPv6-only connected devices, the measurable outcome. They directly expanded their reach in the U.S. market to 3x users.
3 times the users, just by enabling IPv6.
That's what they reported. It highlights an incredibly compelling business case for adoption, doesn't it? Many cellular and new broadband connections are IPv6 first. Making your public endpoint IPv6 enabled becomes a direct, unfiltered path to new customers and broader market penetration. For IMDb, it was literally about growing their audience.
That's a powerful business driver. What about other industries?
Consider Around Home. They're a major player in the home services industry in Europe, connecting homeowners with qualified service providers. Their key challenge was the need for a truly future-proofed network architecture to serve modern clients and adapt to the rapidly evolving internet landscape. Their solution was proactive. They enabled IPv6 on their public-facing endpoints. The remarkable, measurable outcome was a rapid and undeniable shift in their traffic patterns. They reported that nearly 40% of our customer traffic was IPv6 within a surprisingly short amount of time after enabling it.
Nearly 40% that quickly. Wow.
Yeah, it underscores the accelerating global adoption of IPv6 and the undeniable need for public-facing services to be dual-stack. Otherwise, you risk a degraded user experience or even complete inaccessibility for a rapidly growing segment of the Internet's user base. It illustrates that the future is already here for a significant portion of traffic.
Okay, one more. Maybe something different.
Finally, let's look at a U.S. government agency, public sector. Their key challenge was a non-negotiable mandated transition to IPv6 across its nationwide network. This was driven by that U.S. Office of Management and Budget (OMB) memorandum, requiring federal agencies to transition to IPv6 by 2025. No ifs, ands, or buts. Their IPv6 solution was comprehensive. They implemented a comprehensive IPv6 strategy on its extensive AWS cloud infrastructure, touching a wide array of services and network components. The measurable outcome. They not only met the mandate, but actually transformed the agency's network, positioning it at the forefront of technological advancement. Key achievements included seamless integration with existing systems, enhanced performance, security, and scalability across their operations, and crucially, minimal operational disruption during the transition. This case really serves as a robust blueprint for large-scale enterprise adoption, even in the most regulated and complex environments. It shows it can be done smoothly and deliver real benefits beyond just compliance.
What's truly compelling there is seeing these principles play out in the real world, right? Translating directly into business growth like IMDb, meeting compliance like the agency, achieving strategic advantage and scale like Netflix. These aren't just technical curiosities, they're vital enablers for modern, scalable, and resilient businesses. So, quick recap of those wins. Netflix used IPv6 to kill NAT bottlenecks for hyperscale growth. IMDb tripled its reach to new IPv6 first users. Around Home saw nearly 40% of its traffic shift to IPv6, highlighting rapid global adoption, and a U.S. government agency used it to meet mandates while enhancing performance and security with minimal disruption. Powerful stuff. Hashtag, tag, outro.
So in synthesizing our findings from this deep dive, I think it's abundantly clear that the transition from IPv4 to IPv6 is far more than just a technical upgrade. It's truly a fundamental and, frankly, irreversible shift in cloud networking architecture. And this shift is driven by that powerful trifecta we identified. Economic necessity, those IPv4 costs, undeniable technical superiority, no NAT, better routing SLAC, and the escalating demands of modern applications, IoT, 5G containers. We've seen how the escalating cost and finite supply of public IPv4 addresses, combined with IPv6's simplified architecture, the fundamental elimination of NAT in many scenarios, and its native security features, present an overwhelmingly compelling case for widespread adoption. For enterprises navigating this landscape, we generally recommend a pragmatic three-stage roadmap.
Okay, a roadmap. What does that look like?
First, assess. Conduct a comprehensive audit of your existing workloads. Determine their current IPv6 compatibility. Identify any potential dependencies or blockers. Crucially, prioritize services with significant data egress costs associated with NAT gateways for immediate cost-saving opportunities. These are your low-hanging fruit. Second, migrate. Adopt a phased, dual-stack approach for new applications and maybe non-critical services first. This strategy is key because it allows your organization to build internal expertise, refine processes, and gradually integrate IPv6 capabilities while maintaining that crucial backward compatibility with existing IPv4 systems. No big bang needed. And third, optimize. For suitable greenfield applications or as existing dual-stack applications are fully validated and dependencies removed, design and deploy IPv6-only subnets. This lets you fully realize the costs and operational benefits of a streamlined single-protocol architecture, maximizing efficiency and completely eliminating that IPv4 overhead.
Assess, migrate, optimize. Makes sense. And looking further out to the future. Well, the growth of IPv6 traffic, it's a global phenomenon. We mentioned over 40%. Some regions are already approaching or even exceeding 50% adoption. This signals a clear and undeniable trend where IPv6 isn't just an alternative, it's rapidly becoming the default protocol of the internet. We can confidently anticipate an increase in the implementation of IPv6-only data centers and cloud environments, simply to simplify network management by completely eliminating the coexistence challenges and complexities of running dual-stack everywhere. The emergence of IPv6-only subnets within AWS and services that support IPv6-only private link endpoints, these are already early and strong indicators of this accelerating trend. It points towards a truly IPv6 native cloud future.
The writing's on the wall, really.
It feels like it. And the consistent and undeniable link between IPv6 adoption and those emerging technologies, 5G, the ubiquitous Internet of Things, highly distributed cloud-native microservices, it's crucial. The sheer scale and connectivity requirements of these future applications, the ones enabling everything from real-time augmented reality to fully autonomous smart infrastructure and massive AI model deployments, they are fundamentally impossible to support on the IPv4 protocol. It's simply not built for that scale or density. So what does this all mean for you, the listener, as you navigate and build the future of cloud networking? How do you ensure your architectures are not just current, but truly future-proof?
Well, for cloud network engineers and architects today, a deep understanding of IPv6 is, I'd argue, no longer optional. It is, without question, a critical skill and a strategic imperative for designing and operating scalable, cost-effective, and secure cloud infrastructures that are prepared for what's coming next. The data, the architectural insights, the practical guidance we've presented today hopefully provide the necessary foundation for this essential journey into the next generation of networking.
Okay, so before we wrap up, a final thought for you to mull over. Consider this. In a world where the internet is becoming less about simply connecting computers and more about seamlessly connecting everything from tiny sensors reporting on environmental conditions to massive AI models consuming colossal amounts of data, could clinging to IPv4 be the biggest, most overlooked inhibitor to your next big innovation? That's all for this deep dive. We'll see you next time.